Well, I'm the Amateur Logician from amateurlogician.com, and I hope you are having a good day. We're going to be exploring calculus, so to speak, without calculus. And I think this is a pretty cool exploration of rates of change. We can use the tools of algebra to do this, and we're going to think about a parabola. So here is our parabola. It's the simple y is equal to x squared. Now, if we're thinking about an average rate of change, we can think about 2 points on that parabola. For example, let's take the point 0, 0 and the point 2, 4. Both are on the parabola. Now, the average rate of change is simply the slope of the secant line. That is to say, the straight line that crosses both of those 2 points. What's the slope of that line? Now, with algebra, we know how to do that. We know all about slope. But consider that if we pick different points, the rate of change is definitely going to be different. So for instance, let's say we pick, for our next point, we'll stick with 0, 0 as 1 point, but this time let's say we pick 4, 16. And then we have the question, what is the slope of that secant line? In other words, what's the average rate of change there? And if I can get this, at least approximately, I'll be happy. And it's really clear visually, graphically, that the slope is different. In contrast, let's say we have the tried and true linear equation y is equal to x. Well, in that case, the average rate of change is constant. It has a slope of 1. That rate of change is constant throughout that linear line. But as we're moving along that parabola, the rate of change is changing. What can we say about that changing rate of change? So let's first start with y is equal to x, or f of x equals y equals x. We'll create a table of values. This is one way to approach this. So we have our input x, we have our output f of x equals x. So we have the input x, and let's say it's 0. Well, the output is just going to be 0. Input of 1, output of 1. Input of 2, output of 2. Input of 3, output of 3. Input of 4, output of 4. Input of 5, output of 5, and so on and so forth. But now let's consider the change. Let's call this delta f of x. From 0 to 1, plus 1. A change in 1. 1 to 2, well, that's also plus 1. 2 to 3, plus 1. 3 to 4, plus 1. 4 to 5, plus 1. And so on and so forth. Clearly, there's a pattern. And by the way, in calculus, we would call this the derivative. In algebra, we would just say that's the slope. There's a constant rate of change, just of plus 1. In contrast, let's now consider that parabola f of x equals x squared. So we have our input x, we have our output f of x equals x squared. So input 0, output 0. Input 1, 1 squared is 1. Input of 2, 2 squared is 4. Input of 3, 3 squared is 9. Input of 4, 4 squared is 16. Input of 5, 5 squared is 25. And so on and so forth. And once again, let's think about delta f of x. So what's the change here? From 0 to 1, that's just a plus 1. 1 to 4, well, that's a plus 3. 4 to 9, well, that's a plus 5. 9 to 16, that's a plus 7. 16 to 25, that's a plus 9, and so on and so forth. Now here we have something different. The rate of change is not constant. We don't have one number. We don't just have all 1s or all 2s or all 3s. We have a 1, 3, 5, 7, 9, and so forth. So the rate of change is increasing. We might say that the rate of change is getting faster and faster and faster as we move along that parabola as x increases, as the inputs increase. But notice there's an underlying pattern there. And this is the cool thing about thinking about the parabola this way. There's an underlying linear pattern in that parabola in terms of the rate of change. Because we can do this. let's think about the change in the change of f of x. So delta delta f of x. So 1 to 3, that's plus 2. 3 to 5, that's plus 2. 5 to 7, that's plus 2. 7 to 9, that's plus 2. And so on and so forth. Now we have something that's constant. So in calculus, we would say this is the second derivative. In calculus, we would call this right here the first derivative. And right now, with the tools of algebra, we can describe equations of these patterns. Absolutely. So right here, for instance, clearly delta delta f of x is simply just a constant 2. This right here, because you have that constant rate of change, that's a linear pattern. So using our basic skills to construct linear lines and linear equations, we can construct an equation to describe that pattern. So for instance, to be sure, it depends on how we have our starting point. So the y-intercept of this linear equation we're going to derive can be shifted a little bit up, okay? So if you took the derivative in calculus of x squared, you would just get a 2x. But if we're going to represent the first value of change as a 1, and the next as a 3, and the next as a 5, you won't get 2x, you'll get 2x plus 1, something like that, okay? But that's okay. Let's just say we have the first entry as 1. Actually, I'll just say the first entry is 0, comma 1, and the next entry is 1, comma 3. So if we think about the change in y over the change in x, where this is x comma y, and this is x comma y, we get 1 minus 3 over 0 minus 1, which is minus 2 over minus 1, which is just a 2. And in fact, that pattern stays consistent. And then from there, you can construct the equation. So let's say we have y minus 1 is equal to 2 times the quantity x minus 0. So y minus 1 is equal to 2x. So y is equal to 2x plus 1. So that would be one way to describe this pattern up here. Now, to be sure, if you took the derivative of x squared, you would just get 2x. You wouldn't get a 2x plus 1. But in any case, that doesn't really affect the value of doing this procedure right here. I think this is a really cool way to think about rates of change. Without the use of calculus, we can do it with the tools of algebra. There's an underlying linearity to a parabola. Now that to me is pretty cool. And maybe you think it's cool too.